All right. Welcome back to NeuroClarity, the podcast where neurology becomes, well, clearer. I am Onowori Victor, your host, and today we are taking a journey through time. Yeah, that's right. Time travel. But this time, we are going to make it neurological. We are talking about how to estimate the age of a brain blade using imaging. And don't you worry your head if you've never interpreted a CT or MRI before, because we are going to walk you right through it step by step. I want you to grab your mental passport because we are going to decode how the brain speaks through blood and how MRI can help us figure out when the bleeding actually happened. As usual, our case is derived from Ching Chang Comprehensive Review of Clinical Neurology, and we are currently in Chapter 2. We've done questions 1 to 64, and we are currently in question 65. That being said, let's begin with our case. Question 65. Based on imaging studies shown in Figure 2.20, which of the following is correct? Now let us take a look at our imaging. A. This is a hyperacute bleed. B. This is not a hemorrhage. C. This is an old hemorrhage, probably more than 1 month old. D. The hemorrhage is about a week old. And E. The hemorrhage occurred within the last 24 hours. Let us take a look at our brain imaging again. What do you think? Now, quickly, the answer is D. The hemorrhage is about 1 week old. You may ask me, how? How in heaven's name are you able to tell the age of this hemorrhage based on just 3 imaging? Well, let us break it down. We'll start by understanding what the MRI is actually saying. MRI doesn't take photos of the brain like a camera. No. Instead, it listens to how hydrogen atoms behave in a magnetic field. These atoms live mostly in water and fat, and when a magnetic pulse hits them, they wobble, realign, and relax, and we measure that relaxation in 2 different ways. The first is called the T1 relaxation time, and this tells us how fast they realign with the magnetic field. And the second is the T2 relaxation time, which tells us how fast they lose sync or synchronization with each other. Different substances like blood at different stages change how these protons behave, and that is how we get different shades of black, gray, or white on the scan. So, let's meet the cast characters that emerge after a brain bleed, and this is where the real detective work begins. First, T1 weighted images are good at detecting fatty substances and protein. In fact, I like to think of T1 as tissue first, good at detecting tissues. T2, on the other hand, are good at detecting water or edema. T2 as in H2O, T2 for water. Here's a framework you can use to guide your understanding of what we are going to be discussing next. Whenever you have water flowing freely, it shows bright on T2. Whenever you have a substance that is highly paramagnetic, it shows as bright on T1. And whenever you have a substance that is super paramagnetic, it shows up as dark or hypointense on T1 and T2. Now, let's talk about blood in the brain and why it affects MRI differently over time. Hemorrhage blood changes its chemical form and cellular environment over time, and these changes affect the magnetic property of the blood and thus the MRI signal. Remember we said something about paramagnetic, highly paramagnetic, and superparamagnetic? Well, these are the properties of hemoglobin in blood, and these affect the signals of MRI. And remember when we said free flowing water makes T2 bright? This also refers to the motion of water in the cells, and we are going to have a breakdown of this in the upcoming minutes. First, the bleed is less than 12 hours old, it is hyperacute, and the red blood cells are intact. They are bound by oxygen and thus they are called oxyhemoglobin. Oxyhemoglobin is diamagnetic, meaning it has little or no magnetic disruption, and since it's diamagnetic and not highly paramagnetic, T1 will show nothing interesting and it will be isointense on imaging, meaning it will look like a normal brain tissue. T2 on the other hand will appear bright, and this is because it is hyperacute. Blood is still flowing water is still flowing and it appears like a normal puddle of blood, bright on T2. So, hyperacute T1 is iso-intense because we have oxyhemoglobin, which is still oxygen bound. It is not highly paramagnetic. And we have T2 being bright because water is still flowing. And remember, flowing water comes out as bright on T2. Now, things have begun to settle down, and we are now past 12 hours. We are between 12 hours to 2 days, and we call this the acute phase. In this phase, our red blood cells are still intact, the oxygen has been used up, and right now we have something we call the oxyhemoglobin. Now, although the oxyhemoglobin is paramagnetic, it is not highly paramagnetic and thus it will show as iso-intense or normal on T1. How about T2? Remember that right now things have become still. There are no free flowing water. Recall, free flowing water appears bright on T2, and when this becomes still, it reverses. It becomes dark or hypointense on T2. So therefore, in the acute phase, our T1 is iso-intense and our T2 becomes hypointense. What happens next? Next is between 2 to 7 days. Now things have really settled. Our red blood cells are still intact, but something happens. The oxyhemoglobin becomes methemoglobin, and this is highly paramagnetic. Remember, if it's highly paramagnetic, it will come out as bright on T1, and so T1 will come out hyperintense or bright. But what about T2? Everything is still, so T2 remains hypointense. Next, what happens after 7 days? That is between 8 to 30 days. Our red blood cells are no longer intact. They burst, they lyse, and they release their content outside. Now remember, when you release your content outside, things from inside begin to flow outside, and hence T2 becomes bright again and thus hyperintense. How about T1? Remember, something was inside the cells, methemoglobin, and we said that is highly paramagnetic. This content spilling outside will still remain bright because it is highly paramagnetic, and thus T1 remains hyperintense. So, between 8 days to 30 days, that is after 1 week to less than 1 month, you have T1 being hyperintense because methemoglobin has spilled out and methemoglobin is highly paramagnetic, and T2 becomes hyperintense because we have spillage of content outside and free flow of water has resumed. What happens after 1 month? Well, after 1 month, methemoglobin becomes broken down into hemosiderin plus ferritin, which are basically ion breakdown products, and these are superparamagnetic. Remember what we said before? Superparamagnetic substances tends to cancel out signals, so you tend to have a T1 that is hypointense or iso-intense and a T2 which is hypointense and generally very dark. And why is that? These are iron-rich molecules that distort the magnetic fields heavily, and they are like magnetic sponges. They suck all the signals, especially on T2. Let us put it together for our patient. Back to our imaging. Our T1 is bright, meaning we have a paramagnetic substance which is methemoglobin. Remember, methemoglobin can be either inside the cell or outside the cell. It is usually inside the cell between 2 to 7 days and outside the cell between 7 days to 1 month. What's the flow of water? Remember, it remains still between 2 to 7 days, and thus T2 will be dark if this bleed was between 2 to 7 days. And after about 7 days, that is after about 1 week, the red blood cells will lyse, releasing its content and increasing the flow of water. And thus, T2 will appear bright if this image was taken 1 week after the bleed. So, T1 is bright, T2 is bright. This leaves us between 7 days and 30 days. Let us take a look at our options. A, this is a hyperacute bleed. Now this is false because we know that in hyperacute bleed, the T1 is normal and the T2 is bright. B, this is not a hemorrhage. And now that is false. This is a classic hemorrhage. In fact, look at our first image, which is the axial CT. CT scans are pretty good at picking up blood. However, they will never tell us the time that blood was formed. C, this is an old hemorrhage, probably more than 1 month old, and that is false. Remember, if it's more than 1 month old, T1 and T2 will be hypointense. D, this hemorrhage is about a week old. Remember we said this hemorrhage is between 7 days to 1 month and 7 days is 1 week. So option D looks like the right answer. And E, this hemorrhage occurred within the last 24 hours. That is false. And this is not a hyperacute bleed. Neither is it an acute bleed. Remember, for hyperacute bleed, T1 is normal, T2 is hyperintense. And for acute bleed, T1 is isointense and T2 is hypointense. Our answer is D. Anything else? Interpreting hemorrhages on MRI is all about understanding time, chemistry, and magnetism, and your job is just to match the appearance to the stage of the blood breakdown. This tells you how fresh or old the bleed is, and it's kind of like carbon dating, but this time for neurology. So, next time you find yourself seeing a brain scan, ask yourself, what stage of the blood is this? And what does it say about the timing? And voila, you are officially a neurological time traveler. And that's it for this episode of NeuroClarity. If this helps you to see imaging in a new light or time, share it with a friend, a colleague, or your attending. Stay sharp, stay curious, stay clear, and keep bringing clarity to the brain. Catch you next time. Bye for now.